Kronecker constants and cusp forms. So, Professor Pieter Moree, sorry, you can start the talk.
Okay, thank you so much for this introduction. Yeah, it's really a great pleasure for me to speak. And it's also especially nice that this is for the 75th birthday of Michel Waldschmidt. I've over time not spoken so often with him, but already many years ago, when I was a student in the group of Tiedemann and Evertse, there were many talks on Diophantine approximation. And so in that context, I heard the name of Michel quite a bit. But it was a real pleasure several years ago to meet him in a conference in Rome, where he gave a talk that was close to my interest. And I will actually very briefly also say something related to that. So the theme today goes back to Ramanujan, so many things in number theory. And so it is what I'm going to report on is a lot of work by many people, but the motivation is some recent work. So and this recent work is with Alexandru Sirlan, who was 1 year postdoc at the Max Planck Institute here, and with Alessandro Languasco from University of Padua. And yeah, so there is meanwhile on the archive. This is the work is available, and also I'm writing something more historical together with Bruce Burnt. So that's a great honor for me to write something with such a great expert on Ramanujan. There is also a web page available. So just if you look at the article on the archive, you can see that the information for this web page where the programs are available. So let me then start with the historical background. Yeah, so the setup of the talk is that I will give you a little bit historical background, which I personally find quite interesting. Then I tell you something about Euler-Kronecker constants. So those are generalizations of the well-known Euler constant, and yeah, they come in various generalizations. Then we will apply this to Fourier coefficients of cusp forms, and then I will say something about the results, or formulate the results we have, and very likely I won't have much time to say much about proofs. But so this is the idea, the plan of the talk. So everything starts with the first letter that Ramanujan wrote to Hardy. It's of course one of the most remarkable writings in the history of number theory, certainly, of mathematics too, I think. And one of the statements concerns the numbers that can be written as a sum of two squares. And so he's interested, Ramanujan is interested in counting that, and he claims a very precise formula for the number of integers up to x that can be written as a sum of two squares. Well, actually, sorry, he claims a formula for the number of sum of two squares up to large number b that can be written as sum of two squares. So this is the starting point. What he didn't know was that actually Landau, several years before, had actually derived an asymptotic for this counting function. And so the asymptotic involves some constant times x over square root of log x. And yeah, so if we go back to the result of Ramanujan, or the claim of Ramanujan, it's the same constant. And if you look at this by partial integration, the main term is just k times x over square root of log x. So in that sense, the result of Ramanujan, if true, would imply the result of Landau. And the situation might remind you a little bit of the situation with counting prime numbers, because if we count prime numbers up to x, then we know by the prime number theory that it grows as x over square root, as x over log x. That's a well-known result. On the other hand, Gauss, when he was a teenager already, he made the claim that the number of primes up to x should be well approximated by the logarithmic integral, plus a very small error term. And we know from the unpublished manuscript of Ramanujan that indeed he was inspired by this analogy with counting primes. So, but what you can still ask, given those two results, is which of the approximations is better? Is it the one of Landau, just the k times x over square root of log x, or is it the integral? And so actually the first to be interested in this question was Hardy for logical reasons, because he knew both results. And he had a PhD student called Gertrude Stanley, and he asked her to work this out. Now, unfortunately, she made some mistakes, and she came to then what turned out to be a wrong conclusion. But yeah, now we know what the truth is, and the truth is that the Ramanujan approximation is the better one. So the counting function of the sums of two squares is better approximated by the integral than by the asymptotic. And this is some motive for this question, because we're going to look at other counting functions and we're trying to answer this question. Now, one can be more precise, and actually you can look at not only the first order term, but second order terms. So we know that there is a very precise expansion, and actually the claim of Ramanujan by continuous partial integration would imply a similar form. So the difference would be here in the constants. So his claim just implies some very simple formula for the constants. And so, for example, it implies that the first constant here would be half. However, Shanks computed this constant, and it's not a half. So the conclusion here is that this integral approximation of Ramanujan is asymptotically correct. But if you look at the second order term, it's incorrect. What was correct is that he got the first three decimals of this constant, and now these constants can be computed with much higher precision. Now I make a very small digression, because I want to say something, of course, of the work of Michel. So I alluded to us meeting in Rome, and there he gave a talk, and it was about integers that can be represented by an homogenized cyclotomic polynomial. So this is the n cyclotomic polynomial, and you just make it to be in two variables x and y. And then the question is, which numbers can you represent by non-trivial cyclotomic polynomials? And so in particular, he looked at this counting function. And as you could imagine, the main contribution here will come from the binary forms you have here. So for n is 3, this is quadratic. For n is 4, it's quadratic. For n is 6, it's quadratic. So that gives you, in some sense, the main contribution. And then, of course, you have to do something more. But in essence, you use some arguments as before, and then you can get such a counting function, and also you can indicate what those constants are. So this is in some sense similar to what we just saw. Now Ramanujan made further claims beyond the one in this first letter, namely in an unpublished manuscript. And this unpublished manuscript is now was brought out by Bruce Burnt and Ken Ono. And if you just Google for a seminar Lothringen combinatorics, you can actually find this online. So it's a highly intriguing manuscript. It's totally full of formulas in an extremely compact way. So it's something one would have to study for a long time. And actually Hardy made some start with it, but he only worked out some formulas. So it's incredibly rich manuscript. So one of the main players in that manuscript is the Ramanujan tau function. And since for me the Q that you always have when you're working with modular forms is going to be a prime, I just took a Q1 here. But in essence, you have this infinite product, and there you have the coefficients, and those are that's the Ramanujan tau function. And this form delta is called the modular discriminant. It's the most easy example of a modular form. It's of weight 12. But the interesting, so it was known before Ramanujan, maybe 30 years already. But the interesting thing was that Ramanujan was very interested in the arithmetic properties of the coefficients. So basically, he was the first one to seriously think about the properties of those coefficients. And so what he did in the unpublished manuscript was that he wrote them down for several primes. For several primes, he found congruences. And so we will see those primes again. And you might recognize that 691 divides the 12th Bernoulli number. So what type of congruences did he give? Well, if you look at tau n modulo 2, that's very simple to see that the tau of n is odd, even only if n is not square. He looked at it modulo 23, and this was later written down more precisely by Wilton. So there we have a very simple description of what tau of p modulo 23 is. And in addition, he wrote down congruences of this shape, where I realized that I did not define what that is. So this sigma, there will be a function here, sigma k of n, which is the main player in some sense of this talk. So you just count the sum of divisors of n to the power k. So here it's just to the power 1, here it's to the power 3, and here it's to the power 11. So for these primes, Ramanujan looked at how often tau of n is not divisible by q. So, and for those situations, he made a claim very similar to the one of the sum of two squares. And so this is literally what he writes in some case in the unpublished manuscript. It is very easy to see that basically for almost all n, tau of n is divisible by q. Then by transcendental methods, you can get an asymptotic, and well, you can even go beyond that, and you get his beloved integral approximation with a very good error term. So that's the claim in the unpublished manuscript. And yeah, so my aim is to look further at those claims. Yes, I held this unpublished manuscript in my hand when I was in Cambridge. So that was, of course, a very nice thing to remember. And this is a picture I then made of the relevant statement that I just showed to you. There is this type of situation where you ask a Fourier coefficient to be divisible by some prime q. That was studied by Serre using analytic representation theory. So it's quite deep mathematics involved. But we know, and in very great generality, that you can count you can count the numbers of n up to x such that some prime q doesn't divide a Fourier coefficient, and that you will get something of this form. So very large generality, we know that you get this type of asymptotics. And so the ones that Ramanujan considered were very special, since in some sense actually they're very easy. And so for these primes, Ramanujan actually wrote down what this delta of q is here. So if it's a half, then we have here square root of log x. And so actually Ramanujan got all those numbers right. What I did in 2004 was to compute this coefficient C0. And this is a coefficient that's related to the Euler-Kronecker constant, so hence the title. But yeah, all these Euler-Kronecker constants are different from what you would get from the Ramanujan conjecture. So again, the asymptotically, the claim of Ramanujan was correct, but up to second order, it was incorrect. So now let me tell you something about the Euler-Kronecker constants. So the basic one, of course, is the Euler constant, sometimes called Euler-Massaroni constant. So Massaroni was an Italian who got 21 decimals or something, but he made a mistake at the 15th one or something. And Euler did much more theoretical things involving his constant. So in some sense, I personally prefer to call it the Euler constant. So what we're going to see actually is an Euler-Kronecker constant of a number field. So attached to a number field K, we can look at the Dedekind zeta function. So it's just defined similarly to the Riemann zeta function, but instead of summing over 1 over n to the s, you take the norm of an ideal to the power s. And yeah, so as I say, it's basically the same idea as the Riemann zeta function. You can show that you can analytically continue this function to the whole complex plane, except for S is 1, where it has a simple pole, and it also has an Euler product identity. So that's the recapitulation of this Dedekind zeta function. We can look at this Laurent series around S is 1. So there it has some residue. And yeah, since you're interested in class groups and arithmetic data of number fields, then of course you all know that this residue here is in some sense loaded with arithmetic invariance of your number field. So the class number, the regulator, they all come into here. And then in some sense, it's a natural question, what about this C0? Does it also contain some interesting information? So, and the Euler-Kronecker constant is defined to be the ratio of these two. Now that looks a little bit unnatural at first, but yeah, turns out actually to be the better definition. So it's just always better to look at the ratio of those two numbers. So then you can also look at the logarithmic derivative of the Dedekind zeta function. And then in the end, if you think about it, we obtain the following type of result for the Euler-Kronecker constant. So in essence, it's the constant part of the logarithmic derivative. Yeah, so you take this limit and you get this constant here. So this is basically the way I like to think about the Euler-Kronecker constants. So you can do this game for the Riemann zeta function, and then you get gamma here. So there is also an alternative formula for this Euler-Kronecker constant. So it is some limit and it involves this sum over prime ideals going up to x. And what I like about this formula is that it clearly shows the influence of prime ideals of small norm. So if I have a prime ideal of very small norm, it has a big contribution to this sum, and so it tends to shift the constant towards the negative. So if I have many prime ideals, for example, of small norm, then there is a tendency of the constant to be negative. So in that sense, the constant notices something about the arithmetic structure, namely the prime ideals of small norm. And so the most general concept of Euler-Kronecker constant that I will be using here is the Euler-Kronecker constant of a multiplicative set. So maybe the easiest way to define this is in this, what I indicated here as an alternative way. So if a set S of natural numbers, I have the indicator function, so it's 1 if the number is in the set, and it's 0 otherwise. And now if this indicator function is a multiplicative function, then I call my set to be multiplicative. And so by the result of Fermat, we know that integers that can be written as a sum of two squares, that this is going to be a multiplicative set. And actually, we are looking at sets of this form. So you fix some prime q, you have some interesting arithmetic function f of n, assuming integer values. That in addition is a multiplicative function. And then it's a trivial exercise to see that this set is multiplicative if your f is a multiplicative function. So you can define some associated L series, namely in this way. And then if the constant part of the Laurent series of the logarithmic derivative exists, then this is the Euler-Kronecker constant. So it would be a limit of this form for some appropriate alpha. And alpha is 0 in some sense. This would be a trivial situation. So therefore, I want my alpha to be not equal to 0. So then the question one can ask, can I count the elements in S? So I have such a multiplicative set. Then I'm interested in counting the integers up to x in that set. And the answer is, well, we can do that under the assumption that the primes in that set behave in a reasonable way. So this is what I indicated here as condition A. So you count the primes. Yeah, for me, P is always a prime. So you count the primes up to x that are in your set S. And this is some little technical thing. You say y1 minus delta. You get nicer results further on. So this is in some sense the thing to do. Alternatively, what's the interpretation of the delta? This is the density of the primes that are not in S. So in some sense, that's what delta is. And if this condition is satisfied, then we get the following asymptotic and second order term for the counting function s of x. And here we get the Euler-Kronecker constant of the set S. And so now at this point, you might be reminded of the first results I was showing you, where we were looking at the second order term, and then certain constants came up. So these constants are very closely related to this Euler-Kronecker constant. And in certain special situations, and actually we will be always here in a very simple situation, that's namely where the primes in S are in the union of arithmetic progressions. So in such case, then you get always this asymptotic expansion. Yeah, so in that case, by Dirichlet's theorem on prime numbers, a more precise version of that, this condition is always satisfied. So for the most things I will discuss, this result is already enough that it works for the case where S consists of primes in union of arithmetic progressions. So for example, for the sum of two squares, which primes are sums of two squares? Well, it's 2, and the primes congruent to 1, not 4. So, and those have density half. And so the primes not in there also have density half. And therefore we get here x over square root of log x, as we saw initially. So now we can make some competition if you want to. Namely, we can wonder, is the asymptotic of Landau, is that better than the, or not, than the integral approximation that Ramanujan would prefer? So I look at my counting function, and this would be the main term, and this would be the integral approximation. Then I look at the difference, and the question is, what is eventually better? So if x tends to infinity, is it always the case, for example, that this one is smaller than that one? So in that case, we would say that the Landau approximation is winning. Now, if we go back to this condition A, then we can look at what happens to this constant C1. So what was C1? That was this constant here. So yes, so Ramanujan, that's just by partial integration, would give you delta. Landau would give you 0, because we only look at the first term. We saw that the truth is 1 minus the Euler-Kronecker constant for S times delta. So these are the three things. And now the question is, which of those constants is closer to this number? So, for example, if gamma S is 0, then this is delta, and that's what Ramanujan would predict. So actually for gamma S smaller than a half, then this is closer to delta, then it's closer to 0. And so we arrive at the following condition. Easy to remember condition: if the Euler-Kronecker constant of your multiplicative set S is less than a half, then the Ramanujan approximation is better than the Landau one, and it's the other way around if the constant is greater than a half. And if it's precisely a half, then there is no decision. Then you have to look further at higher terms. But I don't know of any such situation. So we are going to look at the situation for sums of divisor functions, this sigma kn, that appear as Fourier coefficients of Eisenstein series. But some more baby example of this is the Euler-Tauschen function. And so together with Kevin Ford and Florian Luca, we wondered about counting the number of integers n such that some fixed prime q does not divide phi of n. This was partly inspired by work of Kenneth Williams and Spearman, who wrote something about that we could improve. So this here actually the new feature is that we look at an infinite family of these sets, and that we can for each of those primes q, we can answer which approximation is better, Ramanujan one or Landau one. And it turns out that eventually the Landau one is better. And the reason for this is that you, if this q here becomes large, this set starts to approximate the set of all natural numbers. And therefore you can expect that the Euler constant start to approximate the original Euler constant. And so this is what you see in this result, that it approximates the Euler constant eventually. But this Euler constant is a 0.5772 and so on. But this is bigger than a half. And this means that then the Landau approximation is eventually winning. Yeah, and a crucial analysis in that work was used a study of the Euler-Kronecker constant for a cyclotomic field. So, and here just to give you some overview of some Euler-Kronecker constants. So this means that we look at how often is tau of n not divisible by 3, and so that was the situation in 2004 for the Euler-Kronecker constants. The Euler-Kronecker constant of a cyclotomic field Q zeta of Q. The method is basically that it behaves something like a logarithm of Q. And on average, it's logarithm of Q. This is what Fouvry showed. Yeah, co-author also of Michel. And then Ihara. Here you see Ihara, known, for example, from the Ihara zeta function and many things. He's an incredible mathematician, I think. But he conjectured on basis of some numerical data of a student, I think, that this gamma of Q is always greater than 0. And the reason is that for a cyclotomic number field, the smallest norm that you can have is just Q. And yeah, and so if Q gets large, then you would expect this sum to be small. And so maybe you would expect this constant to be positive. And what we showed actually is that extremely rarely it could be that that this gamma is negative. So that means that this Ihara conjecture actually is wrong. But it's the set of primes for which it will be wrong is incredibly thin. I mean, we cannot prove there are infinitely many counterexamples. So later on, some other examples were found by Languasco. And if we assume the so-called Hartley-Littlewood conjecture, then actually this gamma Q can become quite negative. So here you see a plot. So as I said, on average, it's 1. And yeah, you see that the distribution is a bit skewed. So this is something that we don't understand. Here you see that also, again, in the histogram. So yeah, so far about this constant. Yeah, since you're interested in class groups and so on, I thought maybe I will say something about Kummer's conjecture, which is very closely related to all of this. So you look at the ratio of the class number of Q zeta Q and its maximal real subfield. And Kummer conjectured that it should go in this way, asymptotically. So it's a very simple function of Q. Therefore, it makes sense to look at the ratio RQ of this ratio of class numbers versus this simple function, which is the right-hand side here. So I just look at the quotient here. This should tend to 1. So why is this R of Q important? Well, Masley and Montgomery, in the famous work in 1976, they determined basically all cyclotomic fields of class number 1. And for that, they used an estimate for this R of Q. So it's not an unimportant quantity. So the associated Dedekind zeta functions, they can be factorized in terms of DSL functions. And then if you use a result of Hasse, you get the following result, which I like, because on the one hand, it has this RQ related to Kummer's conjecture. On the other hand, it has the Euler-Kronecker constant of Q zeta of Q, which is this one, and the Euler-Kronecker constant of the maximal real subfield, which I indicate with the plus. So this formula in some sense combines both things. And it turns out that from the perspective of analytic number theory, this ratio behaves very closely as this function. And the prime sums that are involved, they're very similar. So here, as Granville showed, you get something like 1 over p. In our situation, the function is log p over p minus 1. So it's a pretty similar type of situation. And actually, this was so similar that we used results of Granville. I mean, we is Kevin Ford here and Florian Luca. We used results of Granville from his Inventiones paper where he did this stuff. So this is a nice connection with class numbers. Okay, so now I get to the exceptional Fourier coefficient congruences. So the question is, what's so special about 23, 7, 5, these primes of Ramanujan? And so this is what I call the exceptional primes. And these primes were classified by pretty famous work of Deligne, Serre, and Swinnerton-Dyer. And our starting point is now, instead of delta that we saw before with the Ramanujan tau function, we're interested in the following 6 cusp forms. And so why the 6 cusp forms? Special feature here is that the space here of the dimension of the space of cusp forms is in all these cases one-dimensional. And so your coefficients are integers, are then multiplicative. So you have a very special structure here. And these are the only cases for the full modular group where actually the space of cusp forms is one-dimensional. So these are all those numbers, these are all those forms. And then we have fantastic properties here that were basically conjectured by Ramanujan. And this is, of course, extremely famous developments followed. Only this last one is a fantastic work of Deligne in 1974. And so if you want to read something about this on more elementary level, then this book of the Morty brothers is really nice, I think. So this led to incredible important stuff. But the aspect that I want to focus on is just congruences. And so what Deligne, Serre, and Swinnerton-Dyer did is they classified the congruences. So they basically determined all congruences of this form, and of this form. So that's what I did. And so in the end, you get some finite list. So given the amount of time I have, I think I will be a little bit brief here on this classification. The message is just that they found basically all congruences of that Ramanujan had found in the unpublished manuscript for delta. They found in those cases. So we precisely know what those congruences are, and so you can list them. And it turns out that for small primes, you have many of those congruences. So they're listed in the table here. Then there were for the bigger primes. So you see some real big prime here. There are fewer congruences, but they're all known. So now because certainly I should mention that. What about the results that we derived? So our interest, inspired by these Fourier application, was to look at the non-divisibility of the sum of divisor function. So so how many integers up to x are there such that a given prime q doesn't divide the Kate sum of divisor function? That's basically the answer and the question. And it turns out to be enough to restrict the k to be a divisor of q minus 1. There's a simple argument. So for every q, there's a finite number of divisor functions that you would have to consider. And so that's basically our motivation to do this work for all the congruences found by Serre and Deligne and Swinnerton-Dyer. So I need to say a little bit about some notation, unfortunately. But actually, so we look at the subfields of the cyclotomic field Q zeta m, and then we define K sub m to be the field, the unique subfield of degree Q minus 1 over m. Yeah, so the Galois group is cyclic, so you have a unique subfield of degree Q minus 1 over m for every divisor m of Q minus 1. So these fields will play some role, and their Euler Konica constants. Then the multiplicative order will play a role. So for every prime p, I look at the multiplicative order of p to the r. So the r is the greatest common divisor of k and q minus 1. So in some sense, if you look at the divisibility of sigma k, and so it's more or less the divisibility of sigma r, where r is this greatest common divisor. And then we're interested in the multiplicative order gp of this number p to the power r. And so these are the two sets that we're interested in. We want to look at the non-divisibility. So these are the two main players. We want to estimate those two things. So yeah, and there is some horrible looking sum involved. You can better just look at this simple sum, which has the same flavor. So in essence, you sum over all primes, and then this is the multiplicative order of p modulo q. And you want the multiplicative order to be greater or equal than 2, otherwise this would diverge. So this is just some finite number, very much depending on the structure of Q minus 1. So Ranking in 1961, he determined the asymptotic behavior of this sum. His PhD student Scorfield looked at some related questions. What we did is we looked at the second order behavior, and so you get some Euler-Kronecker constant gamma k comma q, and this is an expression for it. So we just see the usual Euler constant. We see two Euler constants related to the fields that I just defined. I defined this field km. So those constants show up. Then there is some small irrelevant vector, and then there is a horrible sum over prime numbers. So that's our expression for it. Then you can do this also for a variation that would be relevant for the Fourier coefficients. So that's one result, determining this Euler-Kronecker constant. Another result is doing the Landau versus Ramanujan game, and the answer is that for a fixed number r, then if you look at the kth sum of divisor function, and you look at non-divisibility by q, and so we look at all this k and q for which this holds, and r is some fixed number, then if q is large enough, the Landau approximation will win. But a very common case is where k and q minus 1 have greatest common divisor 1. And in that case, we can actually, so this is quite technically involved, we can actually determine all prime numbers where the Ramanujan approximation is better. So yeah, so those were the results, and now let me show how we apply this to the unpublished manuscript. So I remind you of the statement in the unpublished manuscript. So there was the number 1, which is the asymptotic, and here there is the integral approximation. And basically what we did is for all the congruences except one of type 3, there is only one known of type 3, we were able to determine whether the Landau approximation or the Ramanujan approximation is better. So you can precisely classify that. So yeah, and here these are just examples of the constants involved. Especially here, the last one took 6.5 days of computation. So that's really non-trivial to compute that. So I'm very happy to have Alessandro Languasco as a collaborator. Because he's an absolute expert in doing these computations. He has a cluster of computers available. So yeah, so he could compute those Euler-Kronecker constants. Also for the case where Q is smaller than the weight. So here are then some further examples, and I was very happy to see that the constants I had computed in 2004 were actually correct. So yeah, that was our computation. So let me then just finally say, yeah, I can just say a little bit about what type of ingredients go into the proofs. So you have to look at the associated Dirichlet series. So remember that I defined for a multiplicative set this series LS. So you look at the sum over all integers less or equal than x, such that Q does not divide tau of n, yeah, with 1 over n to the power s. That's an important thing, because we have to take the logarithmic derivative of that and to get the Euler-Kronecker constant from there. You have to know how primes split in those subfields of Q zeta Q, which of course is very classical. We have to factorize the Dedekind zeta functions. You have to know how to very precisely evaluate logarithmic derivatives of Dirichlet L functions. And then if you want to know how this behaves for large Q, yeah, then you need to estimate these horrible sums that I showed you. You have to show that they go to 0 with if Q tends to infinity. And also one needs explicit 0-free regions for Dirichlet L series. So yeah, let me then finally say, because maybe it was not so clear to you when I tried to describe this TS. So this is our sum of divisor function, and then we look at this TS, and then you want to write that in terms of Dirichlet L functions. So let me skip here a step. So you have this TS, and then you have some expression for it. And so yeah, then you want to write that as product of the Dirichlet L series. Then the factorization of those Dedekind zeta functions comes into play. So yeah, and then what you find is that a certain power, so the H here is not a class number, this is notation of ranking, certain power of TS to the power to a certain power, you can write in some very simple behaved function in SS1, so a regular function in SS1, times this product of Dedekind zeta functions. And then if you take the logarithmic derivative of both sides, you will find this expression for gamma k sub q. Yeah, so I think I will stop here.
Thank you, Professor Pieter Moree. So, any question? Any questions from here? So, Krishna.
I just have one So if you can go back to classical theorem 2, this was towards the first part of your talk.
Mm. No.
I think you will.
Yeah.
This one, the other slide,
The next one, you meant this? Or?
Yes. So
Yeah.
you gave information about C0 and C1. Do we know anything about the other constants, C2 up to Cj?
Aha, that's a very good question. So in some sense, you can see them as Stieltjes constants, generalized Stieltjes constants. So what Stieltjes did was, if you look at the Riemann-Zeta function, you can look at the Laurent series around S is 1. And so the constant is the Euler constant, and then the higher order constants, they are the Stieltjes constants. Okay. And so in essence, these things are related to that. So basically, they are determined by the Laurent series of your generating series. So I mean, and what I did was the TS, yeah. So you would have your TS, and then you would have to look at the Laurent series, and from there you can compute it. So Serre, in his beautiful article in L'Enseignement Mathématique in the 70s, it's a very beautiful article where he gives many applications of these type of techniques to especially to Fourier coefficients. But I mean, he also looks at these higher coefficients, but they're extremely. I mean, it would be very difficult to get some numerical hold on it. Okay. I guess.
Okay. Thank you.
But very good question. Yeah.
Thank you.
So any other question, online participants?
So maybe, yeah.
Yeah, there is Srijani have one question. Please unmute.
Yes. Sir, what is the significance of 691?
Okay. Yes, 691 is the divider of the numerator of the 12 Bernoulli number. So the question is, so the most famous congruence proved by Ramanujan is, I think I stated, is the congruence modulo 691. Yes, so here we have it. So it's the final one. Tau of n is congruent to sigma 11 modulo 691. Okay, so what's the idea of the proof of this? So you look at the Eisenstein series E12, and so that's a modular form. And on the other hand, there is the cusp form. This is the delta with the coefficients tau of n. But now modulo 691, the constant term in the Eisenstein series, which involves the 12th Bernoulli number, is going to be 0. So that means that modulo 691, the Eisenstein series in some sense becomes a cusp form. On the other hand, the space of cusp forms is one-dimensional. And so that means that there can only be one, so to say. And therefore, these things are going to be equal. That's roughly the idea of the proof. But so the 691 is the divisor of B12. And so some of the other big primes that for the other modular forms, it's related to that. Then instead of B12, you have to look at the primes dividing the 16th Bernoulli number. Yeah. So basically, it follows more or less the same concept. You have an Eisenstein series which modulo a certain prime becomes a cusp form.
Okay, sir. Thank you.
So any other question from the online participants? Please raise hand. Yeah.
Yes, Peter. You mentioned some result of Schofield, which was several
Yes.
years ago. I suppose that the result that you have contained this result of Schofield. Is that right?
Yeah, the score fields. No, it doesn't contain that because I only look at divisibility by prime Q, and she looked at actually prime powers. So
Okay.
so you want to say you want
Yes.
say 691 squared exactly
exactly,
divided.
this one.
Okay, so we don't say anything about that. We just focus on Q, divisibility by Q.
Yes, and do you expect that you can go further and cover
Yeah.
this?
The various variations that one could do, that's very clear. But we were a little bit tired, and otherwise it becomes more of the same. So, but yeah, certainly there are variations possible.
Okay, thank you.
So any other questions? Those who are. So nobody is rising.